So our next speaker is from Virginia Tech, the Department of Mechanical Engineering, and Professor Zhou, right? Professor Zhou, please.
Okay, thank you. Thank you for the introduction. Okay. I'm Lei Zhou. I graduated from MIT 15 years ago, so I'm glad to come back to give this talk. So my talk is about ocean wave energy converter. I have two keywords. One is self-react, another is mechanical motion rectifier. Okay, we're going to say more about that. So the title Blue Dream, people say this looks like Earth, right? Earth actually means this part. Most part is water, right? So more than 70% are water, and actually, like in the United States, more than 50% of people live within 50 miles. So we should be able to make use of the water energy. And for the ocean, there are four types of energy. One is ocean wave energy, and then the tidal energy, current energy. The fourth is thermal energy, temperature difference. Okay, the first three, they call together marine and hydrokinetic energy because this wave, tidal, and current is motion, kinetic energy. Okay, so the first pattern of ocean wave energy dated 1799. Okay, however, for 100 years, there's no progress. Till First and Second World War, at the time, people use ocean wave to power their lighthouse. The true attention of ocean wave come up from the two energy crises. Okay, energy, so in 1970s, in 2000, when the oil price become very high. Okay, take a look at it here, the ocean energy in United States, the different color means the power density. The power density is measured in kilowatts per meter. That means take this here, Boston is around this area. Take this as an example, like 30 or 20. That means 1 meter, if you set in the beach, the wave propagate to you. 1 meter wave, and the total energy is 30 kilowatts, right? Such kind of energy compared with the solar, like 1.5 kilowatts in sunlight, and it's much larger, right? Also, it's much larger than the wind energy density. Okay, so in United States, our government started ocean wave energy pretty late. So here, after 2000, then U.S. government started the ocean energy. Okay, so in 2008, 2012, okay, totally they invest average like $40 million per year. Now, 10 years later now, last year, they double the DOE's investigation. In 2016, DOE create this office, Water Power Technology Office. You say how late we are, right? We are far behind actually some countries like European countries in the ocean wave research, at least 10 years. Anyway, let us take a look what's going on in the United States. We take a look at the industry, university, national lab. Industry, there are about 30 companies. Many are small, almost all the companies are small companies. Okay, only a few people, and the largest is the ocean power technology. They have about 100 people. Okay, so most of the companies count the government support. Okay, so this is industry. On the university side, also, there are very few players. Like at MIT, CCMA, and DQU just spend a lot of time to look into ocean wave hydrodynamics. They didn't directly work on the ocean wave energy. However, they did fundamental contributions to understand the wave dynamics, wave structure interaction. Like WAMIT, the very popular software was initially developed by Professor Dick Yue to look into wave and structure interaction. And in UC Berkeley recently, radar look into the wave carpet, this type of structure. University of Michigan, Jeff look into the control, Mike look into like a wave, current or current introduced vibration to have energy, right? Oregon State and total, and we use together with University of Washington, they create a Northwest Marine Renewable Energy Center, and they do some energy research from design to control, as well as one test site in construction. And in the United States, we have the only functional test site maintained by University of Hawaii, okay? And we involve energy, ocean wave energy harvesting research, and it started about 2010 when I was in Stony Brook University. Then I moved to Virginia Tech. I'm going to talk more about our research. Before that, this nationwide, 3 national labs, they look into ocean energy. Like Cynthia National Lab, they look mostly on the control side, and PNNL side, looking into environment side. And NREL mostly is testing computational fluid dynamics. Okay, so this is just a brief review about ocean wave research in the United States, including the funding and the university, industry, and national lab. Okay. Now, although ocean wave has been so many years, and the wave energy potential is so large, but if we mention ocean wave energy, no one in your mind can have a picture what ocean wave farm look like. Right? If we say wind farm, immediately you have a huge tower with 2 or 3 blades. And wave energy is not mature yet, okay? So there are different type of technology. Broadly speaking, there are floating type, okay, like a water column type, and overtopping type. This is a whole device in the ocean, and it's in vibration, then harvest energy. This is water column, the water get into the chamber, move out. Then the where's the turbine to rotate one direction to harvest energy. Okay, that is just a regular turbine, get water to the reservoir, gravity to generate energy. Okay, so that is the first wave energy farm. It operated 10 years ago in Scotland, but only operated 4 months. Then it stopped. Okay, so utility scale 2 megawatts device. Okay, this device itself is not 2 megawatts. It's in operating array. So why it's like that? Okay, and I want to mention Dr. Facha, okay. And Dr. Facha was a former president of National Academy of Portugal, okay, National Academy of Engineering in Portugal. He dedicated his whole life in the ocean wave research and developed the first European Union wave energy converter, okay. In a major review, he wrote, power takeoff. Power takeoff is the machinery that convert mechanical energy into electricity. Okay, power takeoff is possibly the single most important element in wave energy technology, and underlies most failure to date. Okay, let us take a look at the wave. This is a nice picture, right? And from this picture, you can see the feature of this wave. Okay. It's very irregular, right? You have amplitude change, frequency change, and this second and next second, today and tomorrow, this season and next season will be different. The variation is much larger than the wind, right? So this is the first wave energy farm, the utility scale. The design is like that. They're called Ocean Dragon. It's something like this, just look like my fingertip, right? If this move inside the wheel surface, you will draw this one, the tip, the distance change. Okay. When the distance change, they use that to draw a piston. Then draw the fluid out, then use the check valve system, then drive the generator. That's accumulator. Okay, that is a system like that. It creates a lot of problem because the friction here, high pressure pipe, like a bearing failure. Actually, this system happened is bearing failure. Okay, it's a reliability problem. So let us say our innovation. Okay, and this is a news media report about our work. Okay, and this is buoy. And we have another body. This is ocean wave with surface wave, means here on the surface amplitude is larger, here the amplitude is smaller. And we make use of this relative motion to generate energy. Now, just imagine that way, the relative motion drive ball screw, and the ball screw drive a gearbox, and the gearbox then drive a generator. The gearbox is a very special gearbox. And can you please play this video? You say this ball screw and this gearbox. This two-direction rotation is one direction, right? So we convert the two-direction motion into one direction. What are the advantages? One side, you say the generator rotates at a constant speed at one direction instead of rotation, right? The efficiency is high. Oh, sorry. Okay, start here. Yeah, yes. Okay, and another thing is the reliability is high, and the ocean wave is inside the ocean is very hard to maintain. Reliability is a big concern. Okay, the mechanism, okay, I call it mechanical motion rectifier, is in analog to the electric voltage rectifier. You have AC voltage, positive, negative, right? Output, when you need to charge a battery or charge your cell phone, you convert into DC. And this is exactly the same as the mechanical motion rectifier. The only difference, there are two differences. One side, okay, we use one-way clutch or one-way bearing instead of semiconductor diode, right? Smoothing capacitor become a flying wheel or rotation inertia. Okay, so to do the research, we need to consider the wave energy input and structural fluid interaction, convert everything into mechanical system, then mechanical power takeoff, then convert into electricity and grid system. Therefore, we need to look into hydrodynamics and multi-body dynamics. We need to look into the power takeoff design, and we need to look into power electronics and control. So this is the work scope of this project, right? Design, electronics control, hydrodynamics, and dynamics, as well as test. So this is a 500 watts prototype, PTO prototype we built, okay. And so we put in the test machine, material compression, extension, we get 80%, more than 80% efficiency. As a reference, okay, hydronic system, we build energy converter and similar scale, hydronic system, we get 20% efficiency. Therefore, mechanical energy to electricity output. That not including the loss of the ball screw, the gearbox, and generator, everything, okay. So another thing, as I mentioned, is the dynamics. We talk about two-body system instead of one body. We don't fix this to the seabed, okay. So we can write the multi-body dynamics actually is very similar to whatever we teach to undergraduate students spring mass system. The only difference are, there's three differences. One is added mass, because the water surrounding the buoy is moving up and down also. This is create additional mass effect. We have hydrodynamics damping, they will propagate, then we lose energy, right? The excitation force is also frequency dependent, all the 3 parameters, added mass, hydrodynamics damping, and excitation force. All the other things will be same as the spring mass system. Okay, so we can find the closed form solution to say the best parameter. Okay, For example, the mass ratio. Okay, to generate more power, if this mass is small, you can imagine that way the energy is not much, right? If this mass is very, very large, either this mass will almost no more. You will get the same result of a single mass system, right? That's the best mass ratio. And this mass is usually much larger than that. This is including the physical mass and the added mass together. Okay, so ocean wave energy harvesting itself is a vibration energy harvesting system. To get the best result, you will need to make sure that the excitation frequency and the certain natural frequency will be the same, right? And you will need to match the damping. So, like the electric damping and mechanical damping will be same. Similar as the batteries, you have inner resistance, you have external resistance. You make the two match. Unfortunately, in the ocean wave system, we cannot achieve that. Ocean wave frequency is very, very low, 0.1, 0.2 hertz. This is a vibration system. If you want to achieve such kind of 0.1 to 0.2 hertz, this buoy needs about 50 meters. This is not practical. Okay, so this buoy natural frequency is usually much higher. Okay, another thing is the system will work very well at resonance. Outside the resonance, the energy gets significantly reduced. Okay, so now look at it. Instead of looking like a simple linear system, like a supermass system, our system, one side we have mechanical motion rectifier. On the other side, such kind of mechanical rectifier will create nonlinear rotation effect. That means the input is one direction, output input two directions, output one direction. So it looks like a flying wire, but it's nonlinear mass. As a result, okay, and you can have broad bandwidth energy harvesting. If the resonance is off-tuned, you still have good energy harvesting effect. Okay. Another thing, you look into two-mass system, and through optimization, you will find that the drag damping will have significant influence on the that happened at no period or high frequency. That happened at the high period or low frequency. Okay, so the drag damping will have significant influence to the system. Therefore, you wouldn't be surprised that when we optimize the structure, you will find that the streamline cylinder is much better than such kind of system. I mentioned that this is the only US company, they're large company, okay, 100%, okay. Most of it's just 5 or 7%, even 3, okay. So these companies that have this product, okay. So this will have huge drag damping, so the efficiency wouldn't be high, okay. Anyway, let us say what kind of tank test result, okay. We did the tank test result in University Maine civil tank, and we test one body system, two body system, and a 6-degree freedom system. And this one body system basically is a fixed column, the buoy move up and down. Two body system, the tank is free to move. Can you please click this one? Yeah. No, oh, just click to play. Okay, you can clearly see this body and this body sometimes move out of phase, right? And they are not in phase. You move out of phase, then we can have more energy. The physical meaning is, okay, and this system in between, there's no spring connect them together. So if you look into natural frequency, and so it does mean the combined natural frequency will match the excitation frequency. However, the physical meaning it can be better. The reason is the damped natural frequency will match exactly the excitation frequency. This is why the 2-degree freedom can double the power output. Okay, actually can achieve better. And this is 6-degree freedom system. The buoy can have 6-degree freedom. This tank also have 6-degree freedom. And I skip this video. We have video here too. Okay, so it's fine. Okay, and one important thing is capture width ratio. Capture width ratio means how much energy comes from wave convert into mechanical energy. So this experiment result, we test at irregular wave, and you say wave energy density, that means how many kilowatts per meter, right? We get more than 50% of capture width ratio, means more than 50% of wave energy converted into mechanical energy. Compared with the literature, like NREA's reference model 3, that is the ocean power technology, the system I showed to you, they have about 16%. Okay, so this is much larger higher. The highest that we find in literature is 40 to 50%. Okay, so we also look into the modeling. I mentioned that the design is analog to the mechanical, electric rectifier, mechanical rectifier, right? However, the system inside you have mechanical transmission. It involves friction. It involves compliance. So such kind of system cannot be represented by the ideal diode. We can convert everything in the mechanical domain into electric domain. So that is the conversion. Okay. So this mechanical motion rectifier, if you look into the compliance, this is compliance. This is compliance, and this is friction. Okay, you can put in such kind of electric domain. And in the system, you will have friction. You will have coupler. It involves compliance too. So, so this system you can use an electric domain to model the friction and coupling effect. Okay, and this is motor too. So unlike the buoy and fluid structure interaction, you can also convert into mechanical domain, electric domain, including the frequency-dependent radiation damping, frequency-dependent mass. That is just an electric circle. Okay. Now we can convert everything in the electric domain, including the frictions, viscous dampings, inertia, compliance. With this configuration, we can go ahead to do the control and power electronics design. Okay. This is power electronics. Okay. As I mentioned that ideally, if you want harvest energy, you have to match the impedance. The generator's impedance, it includes the resistor, inductor, right? And if ideally, if you use resistor to match that, and the best resistor is conjugate of these two, so you take amplitude. Now, in this power electronics, we take advantage of this inductor, make it as DC-DC converters inductor. Details, and we have more in the paper. Okay, can you click this one? Okay. Can you click the video? Okay. So this is 1 to 20 scale, and okay, you move too quick. So anyway, it's fine. Okay, time up. Okay, and sorry to let me continue. It's fine. It's okay. Just the next page, please. Just click next page. Is okay. The computer is slow. Okay, just okay. And overall, this is power electronics. The efficiency itself is 97%. Next page, we compared the power output of this DC-DC converter and the pure resistor. You will find that with this DC-DC converter, the power output can be 2 times more. The reason is with this DC-DC converter, we have feedback control. We control the duty cycle, which cancels the effect of this inductor. Okay, so it didn't. Wow. Looking like it. Okay. So let me see. And this is the ocean wave energy system we talk about. And so we also extend such kind of ocean buoy to the wave surge device. And what the wave? So this wave energy surge device, we work under a collaborative project funded by USAID in collaboration with Egypt. Okay, so we would like to use the ocean wave to pump reverse osmosis water for the desalination. Okay, then we use that for the food and agricultural purpose. So we have some video. I'm going to not show the video. This device, this more like that, the wave surge device is special for the shallow water, like that. Okay. And look at this design. This is interesting. Or this end of the almost end of the project presentation. And say this one. This is a motion rectifier I show you. That's a one-way clutch, one-way clutch. Now we add another one-way clutch here. Then what happens is the wheel can drive the generator, okay, and the turbine also can drive the generator at the same time. These two guys will be independent here through this coupling. What I mean, the wheel will not be able to drive this turbine. The turbine will not drive the wheel. However, they drive this shaft generator together. The advantage is we can significantly reduce the peak to average power ratio, since we have two input, and when this is small, this will take a draw. When this is not, when this is small, this is just a combined compensation with each other. LCOE can be significantly reduced. Now my students are doing experiment in Stevens Institute's wave tank in this week. So this is summary. Okay, I talk about mechanical motion rectifier-based ocean wave energy converter. I talk about two-body wave converter design, why it works, because they have combined system. The natural frequency will be able to match the wave frequency. Okay, we did a wave tank test, and actually we also had some ocean test. So ongoing work, we built a 10 kilowatts diesel system. We send to NREA, is in test in NREA's dynamometer. Okay, so I would like to thank the funding support from Department of Energy, National Science Foundation, and EPA. Okay, as well as Virginia State. These are our core PI organizations. Okay, so in addition, wave energy harvesting research, my group also work on different scale, like civil structural energy harvesting and vehicle energy harvesting too, and for sensing applications, small scale energy harvesting. Thank you. Yeah.
Before I invite the questions, could I ask that if authors of paper number 8 are here? 80, paper number 80. So if not, okay. Anyway, so now it's time for questions. So we do have time for questions.
Thanks, Professor, for your excellent presentation.
Thank you.
I'm a PhD student. I have a question. Professor, in your opinion, what's the most promising and affordable and sustainable green technology in the future? And then if I want to know what's the position of wave energy in a set of green technologies.
Okay.
Thank you, sir.
Okay, thank you. And it's a good question. And my answer probably will disappoint you. Okay. And among all the energy so far, wind, solar, right, wave energy is the worst. Okay. The LCOE mostly is in the range average. Okay, global-wide average, the LCOE is $0.69 per kilowatt hour. So usually in United States, we pay utility probably $0.15 or $0.2 per kilowatt hour. That including the delivery charge. And the probably like a Niagara Falls power plant, the utility company pays them cents, 5 cents or no more than 10 cents per kilowatt hour. The system now is nationwide is 0.69. And it take probably another 10 years for the ocean wave can be compete with that can be competed with other type of energy conversion. However, there are some applications then that is available or the market is there immediately. This figure shows like underwater charging, right? It's underwater charging. You just imagine that way. You have UUV. If you have buoy there, you can charge that, right? You don't have alternative modern coal-fired power plant for such kind of function, right? And you say isolated island, you need power, right? You can use ocean wave. This type of device usually is instead of 500 kilowatts, this probably is 500 watts or even 50 watts. Okay, it takes some time to mature the technology. Like wind energy, like 30 years ago, no one can imagine. Now it's so popular, right? Okay.
Yeah, I was just curious too. You go into shallow waters where they use boring instead of doing the mass there to help reduce the LCE. Is that a possibility in the future, or hard to say?
The shallow water we use a wave surge device is shallow water, and deep water the wave particle is more like that. Shallow water is more like that. Yeah, horizontal motion is larger, right? Therefore, for shallow water wave surge device is better. Thank you.